Right, so let's look at our standard reduction potentials. We need some way, some reference, and we can measure relative to each other, but then that's a relative measurement, and it's not going to be extensible to other reactions we might want to look at. So if we want to ask a hypothetical question of like, well, what is the voltage going to be if I've got reaction A and reaction B, I could either build a cell, or we can come up with a table, which is what we're going to do, of a bunch of half reactions and use those and compare those half reactions and do it math-wise without having to get our hands dirty in lab. But in order to do that, I'm going to need some sort of standard to compare them to. I'm going to need what is the sea level, what is my ground level for an electrochemical cell. And a long time ago, people decided that what we're going to do as our reference, our sea level reaction, is going to be the standard hydrogen reference electrode, the SHE, and that's looking at the reduction of H plus to hydrogen gas, and we're going to say that is 0 volts. And things can be higher than that, have a higher reduction potential, or they could have a lower reduction potential. But we're going to say, all right, we need something to say this is our ground level, and we're going to pick this one. Now, why they picked that one, I think it's just because hydrogen is pretty common. It is a pain in the butt electrode to use. I have only ever seen one working because we have to have hydrogen gas at 1 atmosphere and maintain it. We have to have this aqueous solution of 1 molar H plus and maintain it at 1 molar H plus. So we're generating a flammable gas while we're doing this. We've got to have a strong acid while we're doing it. We need some platinum to, it's awkward, right? But the nice thing is once we've established this reaction, we can then go ahead and say, okay, here's another easier to use reaction. We just need to say, okay, relative to this, I'm going to do a little bit of an offset. Right? So the amount of voltage provided by the voltaic cell is determined by the cell potential, E cell. So electrons, like water, are going to spontaneously flow from regions of high potential energy to regions of low potential energy. Right? And we need to define that baseline or 0 potential energy. We're going to use this standard hydrogen reference electrode. Right, so if we have a regular old reaction, like I said, we've got this guy, we're measuring in our voltmeter, what is my anode relative to my cathode? And we're going to say, okay, my cathode reaction, I'm going to make this standard hydrogen reference electrode. And we're going to say that this guy is going to be 0. And we hook this up to this voltmeter, we get a reading, and it says 0.76, which means that the oxidation reaction is going to be plus 0.76 for an oxidation. But when you flip those signs around and you flip this and make it into a reduction, the reduction potential of zinc going from zinc 2 plus to zinc solid would be minus 0.76. You're going to change the sign. Okay. So the measured voltage gives us our standard electrode potential. When we hook it up to the SHE, we can always calculate the overall change in potential as the difference between the initial and final potential energies. So our energy of our cell is going to be our final minus our initial, which is the same thing as saying our cathode minus our anode. And because our cathode is going to be one of our sides for our reduction, and our anode is going to be the other. In the case of our zinc 2 plus and standard hydrogen reference electrode, right? We measured a value of plus 0.76, right? So 0.76 volts is equal to 0 volts because the reduction is the hydrogen minus the potential of the anode. It means that our reduction potential, and your book is really sloppy about this, but this is just the convention, is that when you have these E naught values, they're almost always going to be as a reduction potential. So a reduction potential at the anode is minus 0.76. And it's confusing because really the potential at that anode is going to be the oxidation, which will be plus 0.76. So anode reactions and cathode reactions are opposite in sign, but equal in magnitude. Yep. So So if we look at this, we've got where is our zinc to zinc solid, zinc 2 plus oxidation. right? So we're going from a anodic reaction where we've got our zinc solid going to zinc 2 plus, and our cathode is going to be H plus going to 2 electrons and HS. Our spontaneous reaction is going to be downwards. So we can say that the voltage is going to be minus 0.76 volts relative to that hydrogen reference electrode. If we look at copper, the electrochemical potential of copper is going to be different than that for zinc. So for our reaction, we're making the cathode be hydrogen reduction, and our anode is going to be the oxidation of copper. It's a non-spontaneous process. I got to go up. And so we're going to end up with plus 0.34 volts relative to our standard hydrogen reference electrode. So we're going to get a big old table of lots and lots of different reactions. Right? And this is a standard reduction potential table. And they're just going to say standard electrode potentials. It is for the reduction reaction. Right? So here is our 0 point for hydrogen. Right? Some numbers below this, these guys are all going to be negative numbers, and these guys up above are all going to be positive numbers. Right? And so if you are below hydrogen, you are a stronger reducing agent. Right? Things that are good reducing agents are down here, like lithium. Right? Lithium is a good reducing agent. It's on that left-hand side of that periodic table, isn't it? So lithium over here is a good reducing agent. Up top, on the other hand, things that are positive relative to that standard hydrogen reference electrode. So here is oxygen. Right? Oxygen is up here on our periodic table. Right? These guys are going to be oxidizing agents up top. Right? And for you to get a chemical reaction to happen, you want to get the largest E cell. So something's got to be a reduction, something's got to be an oxidation. You're going to want to combine them in a way, the spontaneous way is going to be the one that gives you the largest overall positive reaction, or largest overall positive E cell, which is going to be the largest overall positive K, as we're going to see. So all these concentrations are at 1 molar. If a reaction involves H plus aqueous, it's going to be a pH of 0 because it's 1 molar H plus. If a reaction involves OH minus aqueous, it's 1 molar OH minus, the pH is 14. If a reaction involves a gas, the pressure will be 1 atmosphere. So we can use this table, right, of E naught values, or standard state cell reduction potentials, that are corresponding to the reduction half reactions with all solutes at 1 molar and gases at 1 atmosphere. Combining 2 half reactions to obtain a balanced oxidation reduction reaction means 2 manipulations have to take place. One of the reactions has to be reversed, right? Because if this table is all reductions, you're going to have to flip one of them to make it into an oxidation. If you need to multiply it, right, to achieve a balanced reaction, your value of E cell isn't going to change. All right, so this is an important concept, that if I double one of these reactions over here, it is not going to double my voltage, which seems very counterintuitive at first, because just about everything else you do, I'm going to double the reaction, I'm going to double delta H. I'm going to double the reaction, I'm going to double delta G. Right? Here, doubling it is not going to change your cell potential. And you're going to get this equation that says, for my overall cell with both parts, we're going to take the reduction potential of the cathode that I look up on the table, and I'm going to subtract the reduction potential of the anodic reaction that I look up on the table. Right, so it's going to be the table value minus another table value. And that's going to take care of the fact that in flipping those reactions around, you switch the signs. So sometimes, and I think this is a very important slide, when your book says this, E naught of the cathode minus E naught of the anode, you're looking at the reduction potential, the table value, the reduction table value, and the reduction table value of the anode and the reduction table value of the cathode. Sometimes you'll see it as E right and E left, right? Because your cathode is going to be on the right and your anode is going to be on the left. I think that is even more confusing, but sometimes you will see it. Right? And that's because of the convention of the cathode on the right. To me, it makes more sense to think of these as the sum of both electrode contributions. All right? So you're going to have red and his blue ox. Well, it's actually Paul Bunyan, but he's red and his reduction blue, there's the ox. So they could be working together. They could be working opposite to each other, but depending on how they're going to do it, it's going to be the sum of both of their efforts. So it's really that the E cell is the sum of the reduction potential, how's red doing, and then the sum of the oxidation potential, which could be positive or negative, but you're going to get that based on flipping that reaction around. So there's a couple of different ways to do it. If you see me doing this, keep in mind that it is not the standard way to do it. The standard way is to say the reduction potential value from the table minus the reduction value potential on the table. Right? So I'm just saying, okay, I need the oxidation potential. I'm going to flip the sign and add them up. Here they're saying, I'm not going to bother with flipping the sign and adding them. I'm just going to bake that into it. And so there's redness ox. So for our galvanic cells involving a half reaction between zinc going to zinc 2 plus and 2 electrons at the anode, and our copper going to picking up 2 electrons and going to copper solid at the cathode, we're going to get an E cell value of plus 1.1 volts. And we can get that just by looking stuff up on the table. So here's some trends and rules. The standard hydrogen reference electrode reduction potential is going to be 0. The half reactions with a stronger tendency towards reduction are going to have a positive value for our E naughts. That's on the table. Half reactions with a stronger tendency towards oxidation are going to have a negative value for E naught reduction. When a half reaction is reversed, the sign of E naught is reversed. So for an oxidation half reaction, if I want to know its oxidation potential, it is minus the reduction potential. When a half reaction is multiplied by an integer, it remains the same potential. So let's do a couple of examples. For we've got a galvanic cell based on the following redox reaction, we're going to take iron 3 plus and we're going to reduce it to iron 2 plus, and we've got copper solid that we're going to oxidize into copper 2 plus. So we've got our reduction over here. Right? And this guy's a reduction for the copper. These are the things you're going to look up from the table. All right. But is this what we're doing to the copper? No. We have to change it. So we're going to flip that reaction around. And when we do, now it is an oxidation. And our sign became negative 0.34 volts. So over here is a reduction. It was plus 0.34. Now it's going to be minus 0.34. Note that the value of E naught has changed. Since each copper atom is going to produce 2 electrons, but each iron atom is only going to accept 1, we're going to need to take reaction 1 and multiply it by 2. So we're going to get 2 Fe's and 2 E minuses. But notice that this did not change. Right? It was 0.77 volts before. It's 0.77 volts still. Balancing those guys, and we're going to combine them together. We're going to have our iron reduction, our copper as the oxidation. Right? I'm going to add these two together, and then I'm going to add these two together. And this is why my way, I think, makes a little bit more sense for me, because if I'm going to write it out as a chemical equation, all I got to do is I'm going to add up my chemical species, right? Put my copper down here and my iron over here, right? And my electrons cancel each other out. My copper 2 plus is my product, and my iron 2 plus is my product, and then I'm just going to add these guys together. Right? So I'm going to add up 0.77 plus negative 0.34, or if you do it the way the book says, you're going to take 0.77, that was from your cathode reaction, and then you're going to subtract the anode's value, right? So this is where that sign is getting built into it, at minus 0.34 volts, and we're going to end up with 0.43 volts as our overall cell reaction. You need to know how to do this. All right, this is on your BAT list, just like that balancing was. All right, let's do which of the following is the best reducing agent. I've got a couple of different options here. Which one is going to be the best reducing agent? Pause, come back. Yeah, it's going to be the zinc. It's the one with the largest most negative value here, so it's going to be the best reducing agent, right? So if you're below hydrogen, you're good at reducing, right? What's below hydrogen? Stuff like zinc and lithium, those guys on the left-hand side. All right, so order the following from strongest to weakest oxidizing agent and justify your decision. If you can't order and explain why, so Cl2 is a better oxidizing agent than Na+. Cl2 is the larger reduction potential. The others cannot be ordered because we don't know what the reduction potentials are, though we can predict that F- won't be easily reduced, although we don't have quantitative proof of that by looking at our tables. You're going to have to look up those table values. All right, so we got a big table value. These tables get even more extensive, but if you find a reaction, you can pretty much pick one out, combine it with another one, and get an E cell value. So a galvanic cell based on the following reaction, we've got aluminum and magnesium solid, and you're going to get aluminum solid, that's the reduction, and magnesium 2+, that's the oxidation. Our two half reactions are that we've got aluminum 3+, giving us aluminum, and this is written as a reduction. These are both the reductions. All right, and what we're going to need to do is we're going to need to flip one of those and make it into an oxidation, and we're going to calculate the E naught. So what we're going to want to do is, if we've got no other guidance that says, hey, you have to make this one a reduction, and the other one has to be the oxidation, we're going to let nature take its course. And when nature takes its course, we're going to want to go for the largest E cell value. So if I'm going to flip one of these, and one of them becomes positive as an oxidation, because they're both starting out negative, I'm going to flip this magnesium, right? Because I'm going to get plus 0.23 volts. And then I'm going to add it to the minus 1.66 volts. Right? The other way would you make this guy the reduction, and you'd end up with a negative cell voltage. Right? So the half reaction involving the magnesium is going to be the one that's going to be reversed. And since this is oxidation process, that becomes the anode. So our potential at the anode is going to be plus 0.37 volts. Since we switch this reaction around, minus E red for the anode. Since the two half reactions involve different numbers of electrons, we've got to multiply them out. But do we change this? Right? No change on that. Then we're just going to add up our two chemical reactions and our two cell potentials. So we'll end up with 2 Al3 plus and 3 magnesiums, giving us 2 aluminum solids and 3 magnesium 2 pluses. You look up the table value and subtract them, or you go back here and you take these two and add them. You're going to get to the same place, and we get 0.71 volts. Right. Now let's have you do one. Calculate the cell potentials for this reaction where we've got magnesium and copper instead. The magnesium reduction potential is going to be minus 2.37. Our copper reduction potential is plus 0.34 volts. Remember, one of these is going to have to switch and become an oxidation. What is our overall cell potential? All right, come back. Cool. It's going to be plus 2.71 because this is the one you're going to make the oxidation. When I do that, that becomes a plus. I just add these guys up together. Boom, I'm done. I get 2.71. All right, so we're going to, E cell determines the direction of any redox pair. For any given pair of half reactions, the current will always spontaneously flow in the direction that gives us the positive E cell. So if we've got this cell made up of nickel and manganese, right, these are both the reductions. They're both written as reductions, right, because it's going from plus 2 to solid and plus 2 to solid. One of them is going to need to become an oxidation, right? One of them's got to become the cathode. One of them's got to become the anode. Which one are we going to make become the anode? Which one do we have to flip? Yeah, we're going to flip the manganese. So our E cell is going to be minus 2.3 minus negative 1.18 or plus 0.9 volts. If you're doing it my way, you're like, okay, I'm going to find out what, make that guy the positive, add them up. Right? Doing that, you got to flip it around to make it the oxidation, right? Now it's the oxidation. So our nickel is going to give us plus 0.95 volts. This is what that cell would look like. So electrons, once we've identified which one is the anode where the oxidation is happening, electrons we know are going to flow from the manganese to the nickel side. The nickel side is going to be the cathode. That's where the reduction happens, because reduction happens at the cathode. All right, let's try one for you guys a little bit. If tin 2 plus is being oxidized to tin 4 plus, which substance can be an oxidizing agent if this is our reduction potential for tin? So which one is going to give us an overall positive cell potential if we know that we're going from and making this guy not into a reduction, but an oxidation? Okay, it's going to be the copper. All right, because this needs to get flipped. So if we rewrite this as an oxidation, now it's the oxidation reaction. We change the sign. The only one that's going to give us the one that's going to give us the most positive number is combining it with the copper. Otherwise, we're going to get a negative cell potential and it's not spontaneous. We've kind of danced around this a little bit, but drawing out those cells is a little awkward. All right, so drawing out a cell, we're going to physically kind of draw out 2 little beakers each time and draw out a salt bridge, and really the salt bridge doesn't contribute that much to our overall reaction. So what we're going to do instead is we're going to write out what's called the line notation to give us a shorthand and much more compact way rather than drawing out the picture each time. And it's going to be used to describe electrochemical cells. The anode components are listed on the left, and the cathode components are listed on the right. Both components are separated by double vertical lines indicating the salt bridge or porous disk, and a phase difference or boundary is indicated by a single vertical line. The concentrations of aqueous solutions should be specified in the notation if you know them. So in this example right here, we've got a zinc electrode. So we're starting off from left to right with our zinc electrode. That's this guy. So we're going to say zinc solid. Then it is in contact with, there's a phase boundary between the solid and the liquid. So we're going to draw a vertical line. And then we've got our zinc 2 plus in solution. And we're going to say what the concentration is. If there's more than one thing, you would do like a zinc 2 plus and then do a comma, zinc plus 3 or something, and you'd say 1 molar or however, whatever the concentration is. You'd separate out multiple liquids by a comma. And then you get the salt bridge, so there's a phase boundary here. That's one line. And a phase boundary here on the other end of it. That's the other line. And then we're into our copper solution. And we're going to give it the concentration. And then there's another phase boundary here where we're hitting the copper solid electrode. All right. So if we've got this cell where we've got aluminum 3 plus and magnesium solid giving us aluminum solid and magnesium 3 plus, we need to first identify which is the reduction and which is the oxidation. So this guy right here, the magnesium going to magnesium 3 plus, or 2 plus, that's the oxidation. This guy, this is the reduction. So we're going to take our reduction and we're going to put it on the right. So our aluminums are going to go on the right. And our oxidations are going to go on the left. Okay. And then we're going to put that double line in between to indicate that it is going to be a salt bridge. So your solids are always going to be on the outside. So to complete our description of our galvanic cell, the cell potential and the balanced equation, the cell potential is always positive for a voltaic cell, where E cell is going to be the cathode minus the anode. The direction of the electron flow is obtained by inspecting the half reactions and using the direction that gives us the positive E cell. And we got to figure out which one is designated as the anode and which one is the cathode. The nature of each electrode and the ions present in each compartment are chemically inert conductors required if none of the substances participating is a good conducting solid. So you might need some sort of electrode that is not going to react with it if you don't have stuff that's a good conductor. So what I want you to do on your own is sketch a cell using the following solutions and electrodes. I got an Ag electrode in 0.1 molar Ag aqueous solution and a copper electrode in 1 molar copper 2+. In your sketch, include the potential of your cell. What is E0 for the cell? Right? Just look up those table values. Figure out which way the electrons are going. Figure out which one is the cathode and which one is the anode. So we want to figure out which is the reduction reaction and which one is the oxidation reaction. And then I want you to do this again, but using a zinc electrode on the other hand, and the copper electrode. And again, check out the electron flow, the direction, which one's the anode, which one's the cathode. Right? So some of those things might change. The anode and the cathode might change depending on what your relative electropotentials are. Well, let's look at another example. We're going to describe completely the galvanic cells based on the following half reactions under standard conditions. We're going to look at silver reacting with iron. So these, remember, are both written as reductions because they came off of our table. So a reduction potential for the silver is 0.8 volts and the reduction potential for our iron is 0.77 volts. Since we have to have a positive E cell value, reaction 2 is the one that's going to run backwards. So we're going to take this and we're going to leave this as the reduction, because reduction happens always at the cathode. And once we know it's the reduction, we know it's the cathode, which means that this guy's got to be the oxidation and it has to be the anode. Our overall reaction is going to be Ag plus and Fe2 plus. Gives us Fe3 plus and Ag solid, right? Because your Ag is the one getting reduced, so that's your little built-in check there. And your cell voltage is just going to be the sum of those, 0.03 volts. So we're adding them up because we flipped it, made it into the anodic reaction, and this guy's my oxidation potential. So if you add up a reduction and an oxidation potential, it's the same thing as taking a reduction potential of the cathode and subtracting the reduction potential of the anodic reaction. Since the Ag plus receives the electrons and Fe2 plus loses the electrons in the cell reaction, the electrons will flow from the compartment containing the iron to the compartment containing the Ag. Right, so electrons are emitted from the anode. Oxidation occurs in the compartment containing the Fe2 plus, hence this compartment is the anode. Reduction occurs in the compartment with the Ag plus, hence that is the cathode. Reduction, cathode, red cat. The electrode in the Ag plus compartment is silver metal, and we're going to have some sort of inert conductor because you can't make a solid Fe2 plus or a solid Fe3 plus, so you're going to have to use something else, and they're going to say, okay, we'll put it in a platinum solid. So it's going to be a platinum solid on the outside, and then inside we'll have Fe2 plus and Fe3 plus. It could have been a carbon, glassy carbon electrode or something, salt bridge or some sort of barrier, and then our Ag and Ag solid. So this is what a physical representation of that cell would look like. The voltage up here, they're using E. They're using this big squiggly E. And that's the same thing for EM. That's the E for EMF or electrical potential. Right? That's voltage. And our electrons are going to flow this way from our anode to our cathode. And then they put in a porous disk. That's the double line. So here is my slide that has these things kind of organized in a how do I keep this stuff straight in my brain. All right. I got all my stuff that's my oxidation on the left, all my stuff that is my reduction on the right. All right. So noticed oxidized, anode, electrons emitted from the anode. Those are all vowels. Current comes from the cathode. Right, because my current is going to go the opposite way of my electrons. Right, my electrons will go one way, my current goes the other way. Thanks, Ben Franklin. The cathode is on the right. Those are consonants, but it's also alphabetical. A comes before C. My anode is on the left. My cathode is on the right. cathode material itself is going to have a negative charge. Right, so minus charges on here because the electrons are going towards that cathode. My anode is positively charged, but it's going to be marked negative, and my cathode is going to be marked positive. Reduction happens at the cathode. Right, cations, which has a little plus sign, are attracted to the cathode, which is marked as positive. So that cat gains mass, right? Because it's going to take those electrons and it's going to eat them up, right? My anion is negative, right? Negative anions, negative things are attracted to the anode because it is positive. Anions are attracted to the anode. It's where the oxidation happens. Oxidation, anode, both vowels. Right, so this is kind of what I'm thinking. If I got one of these things, right, if I can identify a reduction, all the other things come into place. If I can identify an oxidation, all the other things come into place. Right? So the line notation for the cell would be that I've got copper solid on my left with a physical barrier here, and copper 2+ going into my salt bridge, one barrier, another barrier, hence the double lines, then into my Ag+ solution, and then my Ag solid electrode. That's the cathode. So now we're going to talk about work. So work that can be accomplished when electrons are transferred through a wire depends on the thermodynamic driving force behind the electrons. So batteries can do work. We just did a whole chapter that was talking about free energy and entropy and enthalpy. That was really all about work too. Right? We said delta G was your ability to do work. So our driving force, the EMF, is going to be defined in terms of a potential difference in volts between 2 points on a circuit. So our EMF is going to be units of joules per coulomb. So that is our EMF. Our EMF is work-based. It's got joules in it, right? That's our energy. And we're just looking at, well, what's the charge that's associated with that? So our EMF, our potential difference, is going to be related to work. So if we let the current in our little voltaic cell over here run a light bulb for a period of time, what's going to happen? Well, eventually, over time, we're going to reach equilibrium for our chemical reaction, and we're going to run out of voltage, right? Our voltage is going to be zero. Our battery is dead, right? So our reaction will reach equilibrium. Our voltage will be zero. And since at equilibrium, delta G is equal to zero, no change in work can occur, then our system can do no work. It's zero. So viewed from the point of view